Okay, this lab is a pretty difficult lab. Well, it's simple to do, but some of the calculations can be confusing. And I'd be very surprised if you can get this. I've done this lab a number of times myself, and I've been very careful, and it's only been a few times that I've gotten it to work out extremely well. So part of this, you're going to learn a little bit of experimental error, but it gets on a couple orders of magnitude close to it. And what we're going to do is we're going to look at Avogadro's number. Now, what the heck is Avogadro's number? And this comes the idea of a mole. And mole is sometimes referred to as the chemist's dozen. We just use this big number, and this big number is 6.02 times 10 to the 23rd. This is just a huge number. Why do we use this number? It's convenient. It's because that means that 12 grams of carbon-12 is 1 mole. And so we like using grams, so this is the number that it came out to. And then we can use the numbers in the periodic table to get things. And this number should tell you two things. First of all, it's a huge number. Anything raised to 23rd power, that's a big, big number. And the second thing I should tell you, atoms are really tiny. Atoms really are. They're really, really tiny. To have this many atoms, that's a huge amount of atoms. But to have this many atoms weigh 12 grams, that's really, really insignificant amount of matter. That's nothing. And this shows you how to do some of the calculations. I'll verbally walk you through this. And how many grams of water need to have 1 mole of water? And if you look at the periodic table, hydrogen has a molecular mass, or I'm sorry, atomic mass of 1. Oxygen has 16, so this is 2 from the 2 here times 1 plus 16 times 1, because oxygen is 16 and there's no subscript here, but it's assumed to be 1. So 2 plus 16 is 18 grams. And how many molecules of water are there in 1 mole? This is definition. It's 6.02 times 10 to the 23rd. And then how many moles are in 1 gram of water? So it's 1 gram, then you divide this by 18 grams per mole. So there's 1/18 of a mole here. And how many molecules are that? So it's 1/18 of a mole times 6.02 times 10 to the 23rd. So whatever 6.02 times 10 to the 23rd divided by 18 is, which is going to be a little bit smaller. So let's see here. That's going to be around 3 times 10 to the 22nd, if I can do that number in my head real fast. Now, here, and now we're going to try and give an estimate for Avogadro's number by using cinnamon. And this says here how to make some dishwashing soap. And then after you form this dishwashing soap, you take the calibrated dropper. The procedure is here. I find it's about 15 drops per milliliter for me, but I mean it just depends on how you do the drops. I tend to get more 15 per milliliter, so this is 2 milliliters, 25 drops. It tends to be close to 30 for me, but hey, that's me. I don't know what you guys do. So this about 25 drops is in the ballpark. I get 30, but that's me. So whatever you guys get. And so you calibrated this, and so this lets you know how much you have. And then take a petri dish, put 20 milliliters of water, and then put some cinnamon on the surface. And so just put a little tiny bit, so that way it spreads out evenly on the surface. And then you take your dropper, and then you drop in the drops in the petri dish, and then you get a circle. So you get a circle, and then you measure the circle in centimeters, and get a diameter, and then you clean up. And the idea here, if you wonder why are we doing this, we're trying to get one mono layer of of molecules of the dishwashing soap. So a monolayer means one layer. So, and this is very difficult to do. Give you an example: like the stem cells in your eyes, the top 3 layers of your eyes are stem cells. There's a phospholipid bilayer. So let's think that's a fatty molecule that has, so bilayer is 2 layers. So your cell membranes are actually 2 layers, and you're trying to get one that's 1 layer. So you can see this is going to be really difficult. And the drops, and you have this, the diameter of the circle formed, and surface area. So this is pi d squared divided by 4. Just take that number and the surface area there. And now if you have this in centimeters squared, so you take this number here by d is the number of centimeters, so you put it here and you multiply all this, and this is the area about a 1 molecule, and this will tell you the number of molecules per top layer. And here is this will tell you the grams per milliliter. So calculate out here, you get this number here, and then going through here, so the 1 drop, and this is the number of drops. The let's see, the 3 calculation. You have the grams per milliliter. So number 3, you throw this one here, and this is a molar mass of sodium stearate. So 1 drop, and this is, well, this is per drop, so how many drops you had. And then, oh, and I see you have the average number of drops right here. And you come in here, and then this tells you how many moles are on this top layer. Going through this calculation gives you the number of moles. And then you look at the answer for number 2. Here's your answer for number 2. Here's your answer to number 4. And then this will give you some number. It's going to be a huge number. My students tend to get the numbers low. Typically speaking, the numbers tend to be lower. Why they tend to be lower? Well, they kind of bunch up. The molecules tend to bunch up and form different layers. So the numbers tend to be lower than what they should be. And if you get a number that's really off, that's okay. I mean, that's just the nature. You're doing drops in your kitchen, and but you can see here, though. I mean, part of the point just tells you how big this number is. This number is huge, and then you can see that's not there. How many moles are in this methane? So here, you take 0.3 grams. Divided by molecular mass of methane, so 12 for carbon, 4 times 1, so it's this number divided by 16. How many moles are in a billion molecules? So a billion divided by Avogadro's number, which is 6.02 times 10 to the 23rd, will give you this. And here, let's go the opposite way. Mass in grams of that. So this is the moles. You take this number, the number you got for 3, you multiply it by so the molecular mass of H2O2, hydrogen peroxide. This is 2 times 1 plus 2 times 16, so 34. So this number times 34 will give you that. And I know that's a little difficult to see, but hopefully you're following what I'm saying. So once again, be careful. Although you're using soap and cinnamon, so it shouldn't be too dangerous. But please let me know if any issues.